Hello students, once again I am here with the continuation of class 10th mathematics first chapter real numbers. We have done up to exercise 1.3 in the previous classes. Now we are into the last topic of this chapter. And the last topic of this chapter is with another theorem. This has no specific name as such, but this theorem is used to determine whether a rational number has terminating decimal expansion or non-terminating recurring decimal expansion. We know that every rational number P upon Q has two types of decimal expansion. Either this P upon Q will be a terminating decimal or it will be a non-terminating recurring decimal. Class 9 chapter 1. I hope all of you remember. Yes. Now we are going to study a theorem using which, without finding its decimal value, without dividing P by Q and getting the decimal answer or decimal value, now you can say whether this P upon Q is going to have a terminating decimal expansion or non-terminating recurring decimal expansion. This is all about our next theorem. And the theorem goes like this. Let P upon Q is a rational number. Let P upon Q is a rational number where P and Q are coprime. Where P and Q are coprimes. I hope all of you remember what is coprimes. Again, class 9. What is coprime? If two numbers have no common factor between them, they are called coprimes. P and Q are coprime if they have no common factor between them. Or in simple words, we used to say the simplest form of a rational number. In the simplest form of a rational number, there is no common factor between the numerator and the denominator. For example, 2 upon 4 is not the standard form, but it must be 1 upon 2. So whenever we write the final answer of a rational number, normally we used to write it in the simplest form where P and Q are coprime. So I repeat, before we apply this theorem, this is the condition that in the given rational number, P and Q must be coprime. Numerator and denominator should not have any common factor. If there is common factor, then the first thing that you have to do is cut them and change it into standard form. Then only this theorem will be applicable. Now I continue. Let P upon Q is a rational number where P and Q are coprime. If it has terminating decimal expansion. If it has terminating decimal expansion, then the prime factors of Q, what is Q? Denominator. Then the prime factors of Q will be always in the form of 2 power m into 5 power n. See, what is the theorem? If P upon Q has terminating decimal expansion, then the prime factors of Q then the prime factors of its denominator will be always in the form of 2 power m into 5 power n, where m and n are any positive integers. Where m and n are any positive integers. What does it mean? Any power of 2's and any power of 5's. Or in simple words, what does it mean? If a rational number p upon q has terminating decimal expansion, then the prime factors of its denominator will be always 2's or 5's or both 2 and 5. But you will never get a prime factor other than 2 or 5. Understood? I repeat, if a rational number p upon q has terminating decimal expansion, then the prime factors of its denominator q will be always 2's or 5's or both 2's and 5's. 2 power m into 5 power n means any number of 2's and any number of 5's. It can be only 2's or it can be only 5's or it can be both 2 and 5. But nothing other than 2 and 5. Clear? Okay. Now what is its converse? Its converse. If the prime factors of q is in the form of 2 power m into 5 power n, then p upon q will be a terminating decimal. Converse. In a rational number p upon q, if the prime factors of q are in the form of 2 power m into 5 power n, then p upon q will be a terminating decimal. You have to write both the statement. First you write this statement, then you write below that you write conversely, comma, now you write it in reverse form. If p upon q is a rational number where p and q are coprimes, or first sentence can be said, let p upon q is a rational number where p and q are coprimes. Now we have to start from here. If the prime factors of q is in the form of 2 power m into 5 power n, then p upon q will be a terminating decimal. Or then the decimal expansion of p upon q will be terminating. I hope this point is clear to you. So without doing the division of a rational number p upon q, now you can predict whether the given p upon q has terminating decimal expansion or not. Or not means what is the other chance? If it is not terminating, then what is the other possibility? Non-terminating recurring. These are the only two possible decimal expansion of rational numbers. So this is the last theorem and last topic of this chapter. Now there are some questions related to this. Exercise 1.4. Exercise 1.4, question number 1. Without actually performing the long division, state whether the following rational numbers will have terminating decimal expansion or non-terminating repeating decimal expansion. Got it? So in order to check whether the given p upon q has terminating decimal expansion or non-terminating repeating decimal expansion, first of all you have to do the prime factorization of q. No, before that you have to check whether p upon q is in such a form that p and q are coprimes. If not, your first step is to make them coprime. By cutting with the common factor, make p upon q always in the coprime form. Then find the prime factors of q. If the prime factors of q are in the form of 2 power m into 5 power n, then the answer is terminating. If not, the answer is non-terminating recurring. So this is exercise 1.4, question number 1, and the first one is 13 upon 3125. 13 upon 3125. First thing is to check whether 13 and 3125 are coprime or not. Are they coprime? Yes, they are coprime. 3125 has no factor as 30. Then what to do? Do the prime factorization of 3125. Divisible by 5. Again 5. Okay. So here you have to write 3125 is equal to 5 power 5. The prime factorization of 3125, that is the denominator, is done, and we got the answer 5 power 5. And what is the theorem? If it is in the form of 2 power m into 5 power n, where m and n are non-negative integers, means positive integers, that means it can be it can be terminating. So what is the answer here? Since 3125 has prime factorization in the form of 5 power 5, what is the answer? So here the answer is terminating decimal. Reason, the denominator is in the form of 5 power 5. So I told you, if the prime factors of the denominators are in the form of 2 power m into 5 power n, it can be only 2's, it can be only 5's, or it can be both 2's and 5's, but nothing other than 2 and 5. So here we have only 5. Therefore the answer is, therefore it has terminating decimal form. Clear? Question number 2, 17 upon 8. 17 upon 8. We know that 17 and 8 are coprimes. So see the prime factors of 8. Prime factors of 8 are 2 into 2 into 2. That is 2 power 3. Again the answer is terminating. If only 2's, terminating. Only 5's, then also terminating. Both 2 and 5, terminating. Question number 3. 64 upon 455. Do it as homework. In question number 4 there is a change. In question number 4 it is 15 upon 1600. Here note it. Before you find the prime factors of 1600, you have to do one more thing. What is that? 15 and 1600 are not coprimes. So first of all, you have to cancel them and change it into coprime form. Both are divisible by 5. So it must be 3 upon 320. Okay, it is 3 upon 320. Now you have to find the prime factors of 320. If the prime factors of 320 are in the form of 2's or 5's or both, the answer is terminating, otherwise non-terminating recurring. Similarly, there are questions where you have to change it into coprime form first, then find the prime factorization. Question number 6 is very clear, direct. 23 upon 2 power 3 into 5 power 2. 23 and the denominator are coprime. 23 has no factor of 2 and 5. So simply you see, already the denominator is given in prime factorization form. 2 power 3 into 5 power 2. Therefore, the answer is yes, it has terminating. Next one, 129 upon 2 power 2 into 5 power 7 into 7 power 5. 129 has no factors of 2, 5 and 7. So, it is already in the standard form, coprime. Denominator has 2s, 5s and 7. Therefore, the answer is, it has non-terminating recurring decimal. Non-terminating repeating decimal. Next one is 6 upon 15. Again like this. 6 upon 15. They are not coprime, so you have to cancel by 3. 2 upon 5. Now see the denominator. Denominator is 5. So the answer is terminating decimal. Next one also 35 upon 50. 35 upon 50. They are also not in coprime form. Both are divisible by 5. 7 upon 10. 7 upon 10. Factors of, now prime factors of 10. 2 into 5. So answer terminating. Okay. And the last one is 77 upon 210. Again. 77 upon 210. Both are divisible by 7. So divide. 11 upon 30. Now find the prime factors of 30 and write the answer. I hope it is clear to all of you. So the important point is, before doing the prime factorization, you have to make sure that P and Q are coprimes. If not, cut it and change them into coprime, then find the prime factorization. Clear? Okay. Now question number 2. Write down the decimal expansion of those rational numbers in question number 1 above. This is question number 1. Which have terminating decimal. So, in question number 1, you will write the answer like this. It has terminating decimal. Wherever you got this line as the answer, it has terminating decimal. Now go back to question number 1 and take out all those questions where you got terminating decimal. Find its terminating form, decimal form. How can you find the decimal form of 13 upon 3125? You can do it in 2 ways. Number 1, by direct division. Divide 13 by 325. One form is 13 divided by 3125. Okay, ordinary division. Or there is one more method. You have done the prime factorization of 3125 and you got 5 power 5. So we can write 13 upon 3125 can be written as 13 upon 5 power 5. Now, in order to change it into decimal form, there is one more method. We can make the denominator into the form of 10 power something. If the denominator is 10 raised to something, then it is very easy to change it into decimal form. 10 power anything means only you have to put decimal by counting the number of zeros. Since we have already 5 power 5, we can make it into 10 power 5. How? Multiplying the numerator and denominator by 2 power 5, the denominator will become 10 power 5. So we can write it as 13 into 2 power 5 upon 5 power 5 into 2 power 5. Did you understand what is done? Yes. In order to make the denominator as 10 power something, we are multiplying the numerator and denominator by something. Here what is that something? 2 power 5. Now the denominator is okay. The denominator is now 5 power 5 into 2 power 5 is 10 power 5. Now what is the numerator? 13 into 2 power 5. Multiply 13 into 2 power 5. What is 2 power 5? 32. 2 power 5 is 32. So 13 into 32. Four 1/6 upon 10 power 5. 10 power 5 means how many decimal? 5 places of decimal. So 0.00416. Got it? So please learn this method also. One method is direct division. You will get the decimal answer. Second method is this. You have already prime factorized its denominator, that either there will be both 2's and 5's, or there will be only 2, or there will be only 5. If there is only 2, multiply by same power of 5. If there is only 5, multiplied by same power of 2. Now if you have both 2's and 5's, you have to see how many more 2's are required or how many more 5's are required. Accordingly, you have to multiply both numerator and denominator so that your denominator must be always in the form of 5 power something into 2 power the same something. Both the power of 5 and 2 must be same so that it will become 10 power something. 10 power something means 0, 0, 0. By counting the number of zeros, you have to put the decimal. Clear? So these are two methods how to convert a P upon Q into decimal form, provided if it is terminating decimal. Now the last question of the chapter. The following real numbers have decimal expansion as given below. They have decimal expansion. In each case, decide whether they are rational or not. It is a class 9 question. If they are rational and of the form P upon Q, what can you say about the prime factors of Q? Question. If they are rational, so first of all you have to tell whether they are rational or not. And if they are rational and of the form P upon Q, given in decimal form, if it was in P upon Q form, what can you say about the prime factors of Q? Let's see. The first question. Question number 3, first question. 43.123456789. Yes, we know that it is a terminating decimal. After 9, no other digit or no dash dash. So it is a terminating decimal. Every terminating decimal is a rational number. Yes or no need. You can write it is a rational number. Now you see, this rational number has terminating decimal expansion. Since it has terminating decimal expansion, what can you say about the prime factors of Q? It will be in the form of 2 power m into 5 power n. So you can write, since it is a terminating decimal, since it is a terminating decimal, the prime factors of Q will be in the form of 2 power m into 5 power n. Got it? Since it is terminating decimal. Question number 2. 0.120, 1200, 12000, 124 times 0 dash dash. You got it from class 9? This type of decimal numbers are called non-terminating, non-recurring decimal. All the non-terminating, non-recurring decimals are irrational. So question number 2 is irrational. So since it is irrational, this second part of the question does not exist. Third one, 43.12345678 bar. What is a bar number decimal? It is non-terminating recurring decimal. Every non-terminating recurring decimal is rational. So the first answer of the first part is yes, it is rational. So question number 2. Question number 2. 0.120, 1200, 12000 dash dash. It is irrational. It is irrational. And number 3. Question is 43.123456.789 bar. This is called non-terminating recurring decimal. All the non-terminating recurring decimal is rational. So it is rational. But in terms of non-terminating recurring decimal, what can you say about the prime factors of Q? It will not be in the form of 2 power m into 5 power n. So after this you have to write one more line. Since it is a non-terminating recurring decimal, the prime factors of Q will not be in the form of 2 power m into 5 power n. So if the rational number is terminating, then only the prime factors of Q will be in the form of 2 power m into 5 power n. If it is non-terminating recurring, then the number is rational. But then the prime factors of Q will not be in the form of 2 power m into 5 power n. So I hope all of you understood what is taught today. So that is the end of chapter 1, real numbers. So please practice these questions of last exercise 1.4, and please take care of you. Bye bye.